So I have my calculator selected for polar coordinates. I'm going to go to y equals. And then let's start with the sine of theta. And theta, by the way, is the variable for polar coordinates. So you hit the x, t, theta, n. It knows that it's in polar coordinates. So when you click on that, it knows that it's going to put a theta. I have my drawing thing with a dot so I can follow it along. And I want to adjust my window. So it looks like based on what these guys drew, I didn't go in the negative side. So let's look at the window first. So theta going from 0 to 6.28. The steps, I got 0.13. That's probably good enough. The x-min, -2 to 2. It actually didn't go that far on the negative side. So I'm going to, let's put -1 to 1. And then the y minimum, it starts at 0, so we can just leave it at 0, and let's go to 2. 1.5 would probably do, but let's just go do it like this. And then we'll adjust it, because when we first see it, it doesn't look like it's not going to be in that aspect ratio that we want. It's going to be an aspect ratio of the calculator. So let's hit graph. And right now it looks like an ellipse, but if I zoom, there's one of those zoom buttons that allows you to look at it a certain way. If I zoom the correct way, I can see it a little bit better. So let me zoom. Is that square? What number is that? 0? Z square, 5. So if I just go down to 5 or just hit the number 5, then it's going to redraw it, and it looks a lot more like a circle like it's supposed to. But look at what happens, right? It draws it twice. If you have that little thing, you can see it actually being drawn twice. So if I go to window again, and instead of going all the way up to 2 pi, if I just go to pi, so you can either look for pi in your calculator or type, that's not pi, that's e. Or you could type 3.14, since the calculator is just approximating anyways. If you just draw it from 0 to pi, then you would still see that whole circle. Okay? If it doesn't look quite like a circle, because maybe the calculator is approximating too much, let's go back to window. And remember this t step that we saw earlier? Now it's called theta step. If we make that smaller, like 0.05, it's going to take a little bit longer to draw because it's going to plot more points, but it'll look a lot more like a circle because it's more precise. Okay? If you take your t-steps too large, let me change it again, and maybe put something like 0.5. This is going to be kind of ridiculous looking. So it's going to take larger steps and then connect those as lines, and so this is what I get. So that's how the t-step, the step, works in polar and parametric equations. All right? Any questions? All right. So that's our basics of graphing. Somebody mentioned a clover, a leaf, flower thing. So let's actually figure out how this is going to look like. I'm going to change this back. No, I'm going to go back to the y equals. And if you put, instead of sine theta, if you put 3 theta, the sine function, the amplitude, no, amplitude's not going to change, but the frequency is going to change. And so this is going to have to go through positive and negatives a lot faster as it goes around. So when you see that happen, it's going to draw those different flowers or different petals. So I'm going to go to zoom fit this time. Zoom, and fit is down further, I guess. 0. So just hit the number 0. All right. So I guess they didn't adjust my 0.05. And then since I'm in the window, I might as well fix the window. So I'm going to go from -1 to 1 in my x. And then I'm going to go from -1 to 1 in my y also. And then maybe I'll do the zoom square too. Make it look a little bit more. Thanks. And then let's graph it. So notice how it's being drawn, right? It's being drawn. It's not drawing a leaf and then drawing the other leaf. Well, it's drawing the leaves, but it's drawing it in a certain way where if you imagine that stick, that pointer stick, that these guys were revolving around, if you imagine that stick going around in all these angles, it's being drawn out from that stick. And then this goes negative a couple of times as well, so you can see when, try to figure out when it goes negative. Okay? So here are some simple graphs and stuff. Let's take a look at formally define, not define, but formally talk about polar coordinates. So in the little activity that we saw so far, we saw some basic examples, and let me just draw out what they had. R is equal to theta was our first example, and what we looked at was a graph in Cartesian coordinates of r and theta, and a graph on the xy of the r theta combination. And then we saw the sine function with r and theta. And realized that the graph turned out to be a circle, and if you go all the way to 2 pi, it's a circle that's going to be drawn twice. And let's take a look at the circle again a little bit closely. Where's the center of the circle? 1. So the top of the circle is 2. Let's think about that. So it's a half, and then this is 1. Okay? Let's think about the cosine function without doing it on your graphing calculators. When theta is equal to 0, this is my drawing stick right here. When theta is equal to 0, where is r? 1. So we're starting off over here at 1, right? Now, when theta goes to pi over 2, where's pi over 2? So by the time you get to pi over 2, you need to be at 0, right? So as this graph, it's not rotating quickly enough. It's not rotating in live action. So what happens is as this graph goes from 0 to pi over 2, the r value goes from 1 to 0. Right? Now, when my angle is in the third quadrant, in the second quadrant, my values are negative. So I would be going on this side in the fourth quadrant. So I'm going to go from 0 to -1. By the time my angle lands at pi, I'm going to be on the other side, -1, which is back to where I started from in this graph originally. And again, this is a distance of 1 from the origin. It started with +1 and went to -1. I've completed the circle at pi over, or pi. One circle completed. By the time you get to pi. And then if you go from pi to 2 pi, you're going to redraw that same circle again. Okay? All right, so that's the idea of drawing in polar coordinates. And with some of these other functions, like 3 theta, for example, where you get like 3 frequencies from 0 to 2 pi, or you see the sine function 3 times. Is that 3 times? 2, 3. From 0 to 2 pi. Then the graph starts at 0, it draws this curve, and then draws this curve, and then this curve, and then back. So the radial distance here is 1, which means this distance here is 1. From the origin to the tips of those would be radial distances of 1. Okay? So there's a lot of neat pictures that you can draw with polar coordinates. And just imagine your drawing stick going around in a circle, and then you're either going positive or negative on those, on the graph, depending on what the angle is. Kind of like a spirograph, yeah.
When you draw a square?
I think it'll never completely look like a square unless you're, yeah, you can draw. You can draw corners, right? Yeah, you can draw corners. So you can draw squares somehow. Combinations of secant and cosecant, some stuff. Yeah, I mean, if you try graphing tangent on the polar coordinate graph, then see how it's going to look like. So instead of using the graphing calculator, I have this other program called, well, graphing calculator. So this isn't quite a square, but so let's formalize this using some equations, and all you really need are 4 equations, 2 of them really, and then one of them you should, I guess 3 of them. So here's symbolically or algebraically, here's the relationship between polar coordinates and Cartesian coordinates. So you have x and y in Cartesian coordinates, and then you have r and theta in polar coordinates. So the relationship is that your x is going to be r cosine theta and your y is going to be r sine theta, and that is something that we'll have to remember throughout the rest of the semester because that's always going to come up. And then x squared plus y squared is equal to r squared. That's kind of easy to remember because that's something that we've kind of, in a unit circle, r is equal to 1, so it's our standard relationship. But if we're not in the unit circle, it's going to be the radial distance squared. And then not so oftenly used our theta relationship between theta and x and y is that the tangent of theta is y over x. You can think about that as a rise over run. Y is the vertical distance and x is the horizontal distance. So you got the rise over run for, it's like the opposite over adjacent in your triangle in standard position. The thing about the tangent here is that when you're trying to solve for an angle theta, the arctangent restricts you to minus pi over 2 to pi over 2. So if you need to go beyond that, you might not get it unless you actually do the solutions with theta is equal to like pi over 2 plus 2 pi n or something like that. You remember doing that in trig? Anyways, so if we take a look at some examples of what we did, we have, what's a good example? Well, a good example that we didn't really do, aside from Joe mentioning it, is that r is equal to 1. If you have r is equal to 1 and you try to graph that, what you're saying is that it doesn't matter what the angle is, your radial distance is always going to be 1. So that's like taking a compass and then drawing a circle. So this is really essentially a circle. So on your Cartesian graph, you have r is equal to 1, but on your polar coordinate graph paper, you have it going around at the radial distance of 1. So sometimes an idea might be to try to translate this into using these equations, translate this into Cartesian coordinates. And so you have r is equal to 1. You can use this equation over here. 1 squared is equal to x squared plus y squared. And that's just the equation of your circle. X squared plus y squared is equal to 1. Okay, so you'll have a few of those problems where you might need to get creative in trying to draw things out. So I think I have a few more interesting examples here. Let's take a look at a few more examples. And it's just, I think it would be good exercise to try to figure out how this is going to look like in Cartesian coordinates first. And then try to imagine how this thing might look like in polar coordinates. So I have 2 sine theta. That's sine theta is a sine theta. It's a sine function. 2 sine theta would have an amplitude, and then 3 plus that would move it. Now, if you move it 3 units, this is 1, this is 2, this is 3. If you move it 3 units up, here's a question. Are you going to touch the x-axis? So if you move it up like this, you're not going to touch the x-axis. What does it mean when your original graph, before you draw your polar coordinate, when your original graph doesn't touch the x-axis? What does it mean when it touches the x-axis? What? It has a root, but what does it mean with the graph? Y equals 0. Not only that, so what does it mean in your r theta graph? If your r, your radial distance, touches the x-axis, what does that mean? It goes to the origin. So imagine those guys turning the stick again. As they're turning the stick, whenever it touches the origin and goes negative, the guys that are drawing it have to go back to the origin. And then it goes on the other side, right? So in this case, this will never go back to the origin. Okay, so when I draw this graph, I'm not going to hit the origin. Does that part make sense? Now my graph starts at 1, 2, 3. When the angle is 0, I have a distance of 3 away. And then it looks like I'll hit my highest point, a distance of, how far away is that distance? I'm looking at this point when this is at pi over 2, and this is my line here started at 3, and then it has amplitude of 2, so 4, 5. So I will have a distance of 5. So by the time I get to, maybe I need to redraw this 3 over here, 3. By the time I get to pi, if I draw my drawing stick, there he goes. Now it's moving. So if I move it and draw it where it's pointing at pi over 2, I'll have an r value of, what was it again? 5, right? And then when I get to pi, I'll be at the midline again, so I'll be back at 3. And then this will be my lowest point when I get to 3 pi over 2. When I get to 3 pi over 2, what value do I have there? It's -1 if it wasn't shifted. This looks like I'm at +1, right? So that would be +1 somewhere over here. And then I would bounce back up to the midline, which is 3. So can you imagine how this thing's going to look like? So I need to basically connect these points in a nice smooth way. I'll have this, I'll go up to 5, and I'll go back down to 3, and I'll go back to 1, and then back up to 3. Oh, doesn't that look cute? Dented circle. Wow. It sounds a little. It's not as nice as saying it looks like a heart. All right. So this is called a cardioid, named after a heart.
So if we did like negative 2 sine theta minus 3, it would actually look like a heart?
I think if you graph this, it'll actually look like a heart. All right, so when you're doing these problems, try to imagine what the graph looks like originally and then try to draw it out. If you're in a hurry, you can just draw it out. So I'm going to use this program again. So this next one looks more like, so that the heart doesn't go all the way to, it rounds off over here because it's drawing like circle-like things. And notice that between the sine and the cosine, the sine looks like it's going up and down and the cosine looks like it's going sideways, right? So you can notice a lot of those things happening for the different sines and cosine functions. So the 3 minus 3 cosine theta eventually will hit 0. Right, so it looks like it's going to hit 0 when theta is equal to maybe, when theta is equal to 0 and 2 pi, you're at 0. And then what do you think this is going to look like? This one I definitely want to look at the graph first. So 2 cosine, you got the cosine function looking like this. 2 cosine would make it go up by amplitude. And then the negative in front of it would make it go upside down. And then you add 1 to it. So you move it up 1. That's a lot of graphs, huh? All right. The point here is that we're going into the negative territory. So as you're drawing this, you're going to have a negative. So without having drawn it out on your calculators, what do you think this is going to look like? Say, kind of like a heart, goes sideways. Yeah? It goes into itself. Yeah. It goes into itself, whatever that means. It's like a heart that goes into itself. Oh, that's almost poetic. Yeah, there's going to be something inside. So what happens here is as you're starting off when theta is equal to 0, you're at negative 1. So you're actually starting over here on the negative side. And then at some angle over here, which we don't know, which I guess you can find out if you want, at some angle over here you go to 0. So imagine from the back over here going to 0. And then from here to the high point is probably at pi. So from this angle going all the way to pi, you're going to get a positive contribution that continues to grow until whatever the height is here. Anybody know what the height is here? 3? So you're going to go from 0 to a measure of 3 over here. So that's probably going to get that piece of the heart that goes up that way. And then you continue drawing this over to some other angle before it goes negative. And then it's going to go to 0 and eventually go back into itself. That's our phrase now. It's going to go into itself. It's like the heart that was pierced into itself. Cardioid, oid, O-I-D, cardioid. So these are examples of cardioids. And this is a French word with a C that goes down underneath. Anybody here speak French? So what's this? How do you say this word? Limaçon. Or if you're American, you say limacon. It's limaçon. Okay, those are the basic graphs. I mean, there's also those petals. If you take the sine or cosine, instead of having theta, so you can change this into having 4 leaves. Wait, that's not 4 leaves. Five leaves? 6? 6 leaves? That's not 6. What is it? 12. So what do you think is happening to the odd versus the even coefficients here? One is doubled, right? So if it's even, it looks like you have twice as many leaves. If it's odd, you look like there's only as many as whatever the odd number is. But look at it carefully. It's the same number, except it's drawing it twice for the odd ones. Okay? Draw it out in your calculator to see how it's being drawn. So we got these other types of graphs, these rose petals or petals, flower petals or roses or flowers, whatever they're called. Okay. I don't think there's any time to go into the calculus of polar coordinates, but that's what we're going to do next time. We're going to look at finding derivatives. We're going to go back to the idea of dy dx here, and then we're going to look at the idea of finding areas. But instead of finding the area under the curve, it would kind of like, it would make more sense to find not the area under the curve, but the area that it's sweeping as you're drawing this out. So there's a slight difference in the areas that we're going to look at. And we're also going to look at the arc length. All right, so that's what's up for next time. Oh, so homework 10.1 and 10.2 will be due on Sunday. I know it still says February 2nd there, but I'm going to change the date. Okay, so get on those homework assignments.